So I cannot compete with the previous talk on the design of the slides. That was amazing, I don't know, fantastic. But I try to compete on a number of equations. All right, so I would like to talk about a work we did with Kaho and Alex, trying to improve on Davis-Chandrasekhar-Fermi method of determining magnetic field strength. Basically, we would like to take into account the properties of the turbulence where we would like to see and determine magnetic field strength from, and see how properties of the turbulence affect the details of the estimate. So original DCF idea is that the level of fluctuations of polarizations give you an information about strength of a magnetic field, because stronger the magnetic field, more difficult it is to change its direction, and so it will reduce the dispersion in the polarization angles if you observe it on the sky. So that's a directly observable quantity. What you need to do, you need to somehow relate and find the magnitude of the level of the fluctuations in an absolute value, and that you do by relating fluctuations in the magnetic field to the fluctuations in the velocity using Alfvén-like relation. So if you do it on a particular patch on the sky, then you could expect that you could determine the magnetic field strength over this patch somehow. So, and maybe you could vary the patches and you vary determination where you determine the magnetic field. All right, so so that's a summary of a standard idea, which comes back. Do I have a pointer? And the pointer points where? It points here, which can come back to an estimate of a magnetic field. It is a perpendicular one, so you deal with the signals which are integrated along the line of sight. Measurable quantity is the variance of the velocities and variance of the angles of the, say, polarization. But there is a prefactor in principle, so which is not that easy to determine theoretically. And one of our goals will be dealing with this type of prefactors. So there is a fair amount of ideas, very nice and beautiful, but as all zero-order ideas, it comes with a fair amount of caveats and is not awfully precise. So first of all, variances are global quantities. And if you have a limited patch of a sky, it is hard to determine variance in a sense, in a statistical sense, because variance is determined also, well, sensitive to the wavelengths which are longer than the sky patch. So you don't have also kind of a control. Do you determine the variance of the angles and the velocities over really the same scale? Because if you have a significant volume, then you don't know whether on what scales one quantity saturates relative to another. So you are not measuring local fluctuations. So that's probably one of the important estimates, limitations. Well, what you want to do, you want to measure magnetic field as locally as possible, so to know the map of the strength of magnetic field across the sky. So you really don't have any explicit theory for the factor in front, and factor in front seems to be not unity. So first step that we suggest, and it is not an intrinsically not a novel suggestion, is to relate the measurements not over overall variances, but over localized statistical measure, also quadratic in velocity and in angles, such as structure functions. So in this case, you can cast the estimate which we call differential measure analysis, and differential being because it is a local in scale, in a similar form to Davis Fermi measure with a F0 square factor, which is we need to determine, and that is mean our work was done on determining theoretically what it should be, or at least trying to understand what it should be if our medium is a turbulent, and how it relates to the properties of the turbulence in the medium. So as measures which are measurable quantities, you can have structure function of angles. Exact definition will appear later on, and for example, velocity centroids. Okay, so that comes with significant advantages right away. So again, that those things, those structure functions can be determined over the same patch of the sky, and structure functions are not sensitive to wavelengths longer than a patch. So you kind of have a control, additional control, over what scales you actually pick up your statistics. And you get with sufficient angular resolution, and as Susan said, increasing angular resolution is where you need to go to make a progress in this field. You could get to a more local determination of a perpendicular components of a magnetic field in projection. So, but what is important that those structure functions are actually quite understood in statistical theory of turbulence, and that leads to the possibility to say something about F0 theoretically. All right, so let's say that something theoretically. So it's our coordinate setup. So line of sight is this longer one, sky is blue, blue square. We're measuring structure function at some separations. We are not going at anisotropy over structure function or anything, so we'll average over angles. And magnetic field will choose a coordinates. So magnetic field is an XZ plane. So along Y component, it doesn't have, mean magnetic field doesn't have a component. So, but fluctuations do have. Now, when you deal with the structure function at a particular scale, basically, after you integrate along line of sight over distances similar to the scale, accumulation of a signal becomes like a random walk and really not very correlated. So that actually gives you more control about what happens with an integration along the line of sight as well. All right, so well, instead of angles, which is not very nice quantity, you should use Q and U for the polarization angles, or for the measures of polarization angles, and one quadratic combinations of Q and U's translates into this quantity in angles, which is actually nicer behavior than just simply angles themselves, because you can go to larger angles without well, if you reach pi over 4, you're already saturated, but this is taken care of automatically. Now, in our coordinate system, where magnetic field is along the x directions, in a first order of the fluctuations of delta B over B, Q is actually practically equal to the intensity, while U is the quantity which is small, which fluctuates, and that is basically gives you orthogonal perturbations of the magnetic field to the mean one, and that's what gives you the angle. So you could relate, therefore, what you can measure to this nasty construction, which involves this B perpendicular square, which will be our measure in front, as in DCF, but with some integrated properties of a three-dimensional turbulence. And that's your turbulence kind of model here. And it is only orthogonal to the mean magnetic field component which matters. So similarly to for the velocity centroids, it will be line of sight, z direction components, and this is again theoretical quantity, and this is what you will measure later on. So if you put this together, the revised version relates to a measurable structure function. This is your F0 square, which you are supposed to get out of theory by substituting model behavior of the your turbulent model. What we'll find out at the end of the day that if we mostly deal with the subalfinic turbulence, well, mostly actually deal with the subalfinic turbulence, but we find that this quantity is actually mostly depends on alfinic Mach number in projection. So it is a turbulent property dependent quantity, and it is small. It's actually proportional to the square of an alfinic Mach number. So therefore, DCF taken by itself for subalfinic turbulence usually overestimates the magnetic field. Now, if you look in a more detail in a structure, so in the presence of the mean field, fluctuations constitute axisymmetric random process, axisymmetric random field, and can be split in 3 modes. One of them is like an alfinic mode, perpendicular to the wave number and mean magnetic field direction. One is a potential mode along the wave vector, and the third orthogonal mode, which I called of an F-type mode, so which is second mode for the solenoidal motion. So those 3 modes induce a particular structure perturbation, which are very important when you try to make a projection of all the quantity along the line of sight, and it leads to very kind of non-trivial constellations. So in alfinic mode, perpendicular to K in magnetic field is almost always alfinic mode. But what are the other 2 depends on the properties of your plasma. And for a high beta plasma, F mode is actually slow mode, and potential mode is a fast mode. But if it is not a limit of very high beta, then there is a rotation between the 2. But this is just algebraical expansion of the axisymmetric field. And what you find out very quickly is that everything which is important for us actually is not sensitive to potential mode at all. So it is sensitive only to 2 solenoidal modes, which in a turbulence language, when you have a particular model of a turbulence, one of them will be alpha mode, and the other will be some combination of slow and fast modes. But notice all these complicated angular dependencies. Okay, so let's look at a particular example of what happens. So imagine that you have a purely alfinic mode, alfinic turbulence, and you take the case which everybody loves, many simulations shows you when magnetic field is just perpendicular to the line of sight. It lies in a just across the sky. Then when you integrate over sufficiently long line of sight your signal, what you find out that you kill all wave modes which actually have that component. So you end up only in the limit, asymptotic limit of modes which are also perpendicular to the line of sight. So alfinic perturbation in this case will be pointing straight along the line of sight. And that's it. So you can rotate the K on the plane of the sky, alfinic fluctuation delta B, and V will be pointing only straight along the line of sight, which means that alfinic mode doesn't contribute to angle fluctuations at all in this limit. So it's a perfect constellation of a contribution to polarization fluctuations. And that is actually one thing which always surprised me. You look at simulations which has this configuration, and they plot directions of the projected polarization, say, and what you see very small angle fluctuations usually, much smaller than MA that you expect it to be. And that is basically often a projection effect. Now, if you go to a now more realistic turbulence, you don't have only alpha mode, but you have 3 mode in a possible combination. And if you look at the high beta plasma, then the fast modes, which are potential, don't contribute to your measured things. But alpha mode do. So this is a case of angles close to perpendicular. So alpha mode contribution to angles for near perpendicular direction is very much suppressed. And so, but it dominates the velocities, because you need line of sight velocity. This is exactly direction of motion, alpha mode in this case. So for the angles, you rely on a slow mode. And now the question now always arises, if you make a measure, it all depends on what is the ratio of the energy in two modes. So two parts of a signal in DCF type of measurements actually come from different modes in your turbulent plasma. And you would think that if you take, for example, case of a strong turbulence, which is where slow modes and alpha modes are nearly in equipartition, you say, okay, fine, it's a different mode, but it's the same energy, so it will contribute kind of the same. But that's not exactly how it works out, because if you look at this case, then the power distribution in your different modes is actually also anisotropic in anisotropic turbulence, and it prefers fluctuations which are perpendicular to the magnetic field and suppresses the one which is alongside of the magnetic field. So the best configuration for the slow modes will be the one where wave number is perpendicular to the magnetic field. So that would have the highest amplitude. But in this case, the fluctuation itself is actually parallel to magnetic field, and again does not contribute to the angle. So your answer comes from some intermediate cases which are not most high amplitude, and you have suppression. And so at the end of the day, what you find that your F0 is proportional to the alpha Mach number for alpha Mach number less than unity. And this is valid for perpendicular and, configuration, but also under some angle. So you could go maybe not to 45 degrees, but over reasonable amount of angle to have this answer. Now, if you go for a low beta plasma, situation is more complicated because now you have a fast modes, and they're not purely potential, so they give their contribution. But you find that again, alpha modes dominate velocity, but now fast modes dominate the angles in configuration, which is again closer to perpendicular, but not exactly perpendicular. Again, up to 45 degrees maybe. So your F0, a factor which will be in your estimate, is actually directly the ratio of the amplitudes in the fast mode versus alpha modes. And here, I don't have any theory for that quantity. And probably by this stage, Cajo is thinking, I spent so many times doing simulations for this paper. It took like 20 pages, and there is not a single simulation being mentioned. Right, so here it is one. So we'll go actually in a suite of simulations which Cajo ran, and what we find out that it is a little bit driving dependent, but there is actually a dependency on an amount of a fast mode versus alpha modes with a MA. So it's actually slightly grows with a MA, and no, it's a MA like 1/2 maybe. So maybe a bit slower, so it needs to be looked at in detail. So now we have our prefactor, which is itself MA dependent, and basically MA is not measurable thing, so we're not doing very well. But you could refer it back to the more measurable quantities and be perpendicular itself. So it's actually implicit equation which contains be perpendicular in the phase 0 as well. And what you could do, you could refer it to the velocities of the injection scale, hoping that maybe you can estimate them somehow. If you do that, you replace MA perpendicular by the ratio of the velocity, alpha velocity and injection scale velocity with angles, which can be now written with alpha relation, again through B perpendicular, and solve it, and find out that our measure is actually have different power of the ratio of the two structure function, not unity for B square, but power which is slightly different from unity. And for example, for high beta, it is like a square root, and for low beta, it's maybe more like 2/3. So with, however, coefficients which for the model distribution of the turbulence is much better understood. So that is actually theoretical questions. Well, no, this one is more numerical question. This is theoretical. This is a whole question. And basically, that is where I stop.
Thank you very much, Mordecai.
So I love the idea of using a limited patch of sky and quantities that can be measured in that patch. But if you still have an anisotropic flow, and of course I'm thinking about accretion, that's still going to distort the velocity perturbations, isn't it?
Yes,
well, I guess maybe the field perturbations. But
yes, it will. So currently we were using just angular average statistics. So we did not try to measure anisotropic structure function or select any other preferred direction. But yeah, that is complexities which will, of course, play a role, yes.
Alex would like to comment, I think.
I would like to address this
Just don't ask me questions.
Because we can use, as we did in the paper, we have the high order structure functions, which can remove regular shear.
Yeah, so basically 2-point structure function removes constants, right? And you can remove slopes with a 3-point structure function.
James.
Thanks for this talk. So as far as I understand, this method will work for subalfanic turbulence.
Yes. Yeah.
How confident are you that the ISM that you're interested in is subalfanic? I think, if I think it's subalfanic, I'll use. If I don't think so, I don't use.
Do you mean that?
Or I use and I'm making mistake. Right?
Well, I mean, if you go to smaller scales and then it's even driven as a super-alphanic, will eventually go to subalphanic at small scales, right?
That's true. That's actually that's a very important comment. That if you look at smaller scales, then even if you are superalphanic at large scale, it's actually becoming more subalphanic.
I totally agree, but how small do you have to go?
Well, that would depend on your alpha and Mach number in a way. So you're running a little bit in circle. But
so I guess similar to the sonic scale, there is alphanic scale. Yeah. And
I'm not sure whether this is a question or a comment. I actually would like to at least have some little bit of extended discussion on how this particular paper is different from Raphael's idea of B proportional to 1/square root MA. No, yeah, probably like that.
Okay, well, that's a good point for a discussion. We have a discussion time, right?
Sure. I want you to.
Is she coming? Is she not coming?
He should be invited.
So I have a question. So we know that DCF, the traditional DCF, usually give overestimated magnetic field strength. And just want to understand how this method you tackled, how much it will improve the technique.
Well, but basically, in the regime that I consider, we consider an estimation is basically proportional to inverse MA. It's an MA factor for with perpendicular, which is in front, right? So there is some numbers like 1/√2 or something, but overall, if you have low MA, you'll be estimated by a few factors of U, right? So
I mean, if you want to apply this modification to observational data, like what observers need to, the observables need
they need to measure two structure functions, and they need to have an idea in a final formulation of velocity at the injection scale or energy at the injection scale, because that came back to us.
Okay. Yeah.
Or intensity. Yes.
Okay, so if there are no other questions, let's thank the speaker again.